In this tutorial, we will talk about exponential distribution. Exponential distribution. Exponential distribution is a continuous type distribution. It describes the length of time between two successive events. And the events should occur independently at a constant average rate. Also, the exponential distribution is usually the first guess for modeling the waiting time in different problems. For example, the time between customers enter a shop, the time that a light bulb lasts before it is out of function. To begin with, we should know the density function and cumulative distribution function of the exponential distribution first. Let x follows the exponential distribution with parameter lambda that is larger than 0. Then it can be denoted like this. And the probability density function of x and cumulative distribution is as following. Noted that the value of x should be larger than or equal to 0, otherwise the functions of x equals to 0. In fact, the cumulative distribution can be obtained by integrating the density on its support, which is x greater than 0. And here are the steps of showing how to derive the cumulative distribution function of x from its density. This is the graph of the probability density function with different parameters. The change in shape of the exponential density for different lambda can also be demonstrated by our program. You can find the interactive R codes for the density plot in the learning module of exponential distribution. Relationship with Poisson distribution. Actually, the exponential distribution and the Poisson distribution are closely related. Poisson distribution is modeling the number of changes in a time interval. But the waiting time between the successive changes can be modeled by exponential distribution. Suppose there is a sequence of events follows Poisson distribution with mean lambda, let x be the waiting time of first event occur. Since the probability that the waiting time of the first event is smaller than x is just the complement of the probability that there is no event occur in the time from 0 to x, we obtain the cumulative distribution function of x by the Poisson PMF. After differentiate the distribution function and we can obtain the PDF of x, which is the same as the aforementioned exponential distribution PDF. Thus, exponential distribution can be used to model the waiting time until the first changes occurs, where the number of changes in a time interval follows the Poisson distribution. And the meaning of the parameter lambda is mean number of change per unit time. There is a simple example to show the relationship. In a college, telephone calls enter the switchboard on average of 2 hours. So, the number of telephone calls received in 2 hours follows the Poisson distribution with rate equals to 8. But the waiting time of the first call follows exponential distribution with lambda equal to 4 per hour. Memoryless property. When W is a continuous random variable whose values lie in non-negative real numbers, 0 to positive infinity, we call W is memoryless if for any s and t that are larger than 0, we have the conditional probability that W is larger than s plus t given W is larger than s, equals to the probability that W is larger than t. Indeed, the exponential distribution is memoryless. What is its meaning? Let's explain with an example. Now we are waiting for a customer to reach our booth and the waiting time is modeled by an exponential distribution. If we have waited for the customer for s units of time, what is the probability that more than t extra units of time to wait for the customer? The answer is no matter how much time, denoted as s, we have waited for, the time, denoted as t, needed from now to wait for the customer will follow the same exponential distribution as if at the beginning. In fact, we can show the memoryless property by some simple arguments and algebras. And here is the detail. The exponential distribution is the continuous analog of the geometric distribution because they are quite similar in some senses. For example, geometric distribution describes the number of trials needed for something happens, such as observe the first success, while exponential distribution usually describes the time needed for something happens, such as observe the first customer reaching the booth. Note that both geometric distribution and exponential distribution are memoryless. Mean and variance. Let x follows the exponential distribution with parameter lambda, then the mean of x equals to 1 over lambda. Before the direct proof for the mean, we need to show that as x tends to infinity, this expression, x to the power of nth times the mathematical constant e to the power of negative lambda times x, equals to 0. Where n is a positive integer. This can be proved by using the L'Hospital's rule as following. Differentiate both the numerator and denominator repeatedly for n times and we can remove x from the numerator. Since now x is approaching to the infinity, therefore the whole fraction representing 1 over infinity, which has the value 0. Then, we can prove that the mean of x equals to 1 over lambda. By the definition of expectation, we have to evaluate this integral to get the mean of x using the integration by parts technique. We obtain this. Then, if we put n equals to 1 to the expression discussed in the previous slide, we get the answer. Moreover, the variance of x equals to 1 over lambda square. Firstly, we find the value of expectation of x square first. By the similar manner on last slide, putting n equals to 2 to this expression, we have expectation of x square is equal to 2 over lambda square. And using the formula that variance of x equals to expectation of x square minus the square of expectation of x, we get the answer again. Now, it is your time to try some exercises. This is the end of this session. Thank you for watching.